So let's get started. Let me remind you of the important business announcement, which is party at Bill's house. I believe his parents won't be there. Stereo system. I heard there was going to be wine. Oh, and food. Gotta be there. Does he have a pool?
But your house isn't that far.
I heard he did, but you have to look around for it. Okay.
Okay, you're cut off.
Brian Skyrms.
Thank you. Pleasure to be here. I've known Bill for a long, long time. I remember a party in his living room in which I learned about Newcomb's problem for the first time. Isaac was there, Henry Kuyper, Dick Jeffrey, right? Paul Nazareth. There were David Kaplan. There were vigorous debates, pro and con, about what was Newcomb's problem. Bill got me interested in game theory when I visited up here. It showed me Schubach's book on game theory and economic modeling, and after that, the two of us went to lots of game theory conferences together. I'd like to do something just for old time's sake. Does it bring back memories, Bill?
It's gonna start the sprinklers.
If they are.
I don't think you want to do that.
Think it'll trip the fire
I
alarm?
don't think you want the risk.
Plus your laptops.
Remember the conference in Binmore when
Yes.
he was? Yes. All right.
You better get the British background.
Put it on the floor.
Blow
A
it.
little worried, speed up. Okay, so in honor of Bill, I'd like to give a talk on equilibrium selection, signaling games, right? If you're the problem about equilibrium selection, that's what Bernie the Dollar was about. I won't explain it, but
I thought you were going to do it in the time.
no.
Well,
But equilibrium selection is a problem where you have lots of equilibrium selection. No better place to discuss this but in signaling games. And I'm going to talk about dynamic considerations in equilibrium selection. And give you some interesting examples, not a big survey, but just something. So we start with signaling games. Invented, to the best of my knowledge, by David Lewis. If you talk to economists, many will try to resist this, right? Because David did it first, right? but he really did. Here's the simplest Lewis signaling game. There's one sender, one receiver. There are two states of the world, two signals, and two acts. The sender observes the state of the world, chooses one of the signals, sends the signal. The receiver chooses one of the acts, conditional on seeing the signal, right? And the act has payoff consequences for both the sender and the receiver. We'll assume that the states are equal probable, so the process is nature flips a fair coin to decide the state. The sender observes the state, sends the signal. The receiver observes the signal, chooses an act. And we'll assume that there's strong common interest between the sender and the receiver. That is, one of the two acts is right in that it pays off both of them for state 1 and 0 for both of them in state 2. And the other is right for state 2 in that it pays off both of them in state 2 and 0 in state 1. So that's the simplest Lewis signaling game. And there's a signaling system, equilibrium, and there are other. So that's a very simple game, but there are lots of ways it can be generalized to make it more interesting. The states might not be equiprobable. That's one of the first things to think about, unless you want to load everything up with symmetry, because which is Lewis wanted to do, because he wanted everything to be conventional. So he wanted the setting to be as symmetric as possible, so there couldn't be anything that gave you a hint that one convention is better than the other. But in lots of signaling games, states aren't equiprobable. There could be more state signals than acts, so the first generalization is n states, n signals, n acts. There's no reason why the number of state signals and acts should match one another. Right? So the second generalization is different numbers of state signals and acts. We could relax the common interest to have different kinds of payoff functions. Costly signaling is just one way of doing this, right? If you do costly signaling, that just means that you add something to the payoff functions. And then analyze it as a signaling game. Finally, you might say, well, we want not just one sender and one receiver, but lots of senders and lots of receivers that can be strung together in some sort of a network, and the signals can then interact over the network. So those are all interesting generalizations, and I'll talk about some of them. So moving right along here. Part 2 is equilibrium considerations. So we're talking about equilibrium selection. So we need to survey equilibria in these games. And here's a picture blown up a little bit so that you see pixels of John Maynard Smith in his garden. I'll be interested, at least in one strand of this, in evolutionary considerations. So Maynard Smith introduced the notion of an evolutionarily stable strategy, which is a strategy such that the whole population does it. Any mutant would do strictly worse. Any epsilon mutant would do strictly worse than the population than the natives. And this is generalized to an evolutionarily stable state, right, which applies to mixed states. And you can think of this as a mutant with a mixed strategy, a little different from the population proportions as the test case. Okay, so there's one way to try to select among equilibria by looking at equilibria that have special properties. Not all particular equilibria are evolutionarily stable, and I'll mostly talk about evolutionary stability. So let's start with the simplest Lewis signaling game, 2x2x2 states, probable, pure common interest. There are two isolated signaling system equilibria, both one in which signal 1 means state 1, signal 2 means state 2, and the other that you get by computing the signals. Right? And they're both evolutionarily stable strategies in Maynard Smith's sense. And then there are a bunch of other equilibria called pooling equilibria, in which no information at all is transmitted. And those are equilibria in which the sender ignores the state and the receiver ignores the signal. And what does ignores mean? Ignores means the sender sends the signals with probabilities that are independent of the state observed. And those could be anywhere between 0 and 1. And likewise, the receiver chooses the acts with some fixed probabilities that are independent of the signal received. And those can go between 0 and 1. So we have a whole square of pooling equilibria in the simplest game. And none of these is an ESS, of course. Can't be. The square itself is not an evolutionarily stable set, general states, and so on. So equilibrium selection seems to select out the signaling system. What happens if the states aren't equiprobable? We still have two isolated signaling system equilibria, the same ones as before. have no longer a square of pooling equilibria, because now if the receiver isn't getting any information from the sender, the best thing for the receiver to do is to do the act that pays off in the most probable state. So the square collapses to a line of pooling equilibria. And as before, none of those are evolutionarily stable, and the line as a whole isn't an evolutionarily stable set, so we seem to have some nice equilibrium selection going here using rigid spin. If we move to n states, n signals, and n acts, then we could get all of the foregoing phenomena that you got in the 2x2x2 case, plus connected components of various kinds of partial pooling equilibria. Now, partial pooling equilibria are when the sender lumps some states together, right? But not all of them. If you lump them all together, that's pooling, right? So the simplest case might be in state 3, send signal 3, get signal 3, you do act 3, but the sender and receiver pool as before, right? On the other two states. So again, only the signaling systems are evolutionarily stable. None of the partial pooling or total pooling stables are evolutionarily stable. Now I'm moving along to a little more generalization where there's a mismatch between the number of states, signals, and acts. And here we have an extra signal. Right? We only need 2 really to get efficient information transfer, but we've got 3. Okay? So now there are lots of ways to get perfect information transfer between the sender and the receiver. Okay? One way would be for all the signals to remain in play and for 2 of them to be synonyms, right? So in one state, the sender sometimes sends one of them, sometimes the other. The receiver recognizes both of those as telling him that's the state and does the right act for that state. Right? Or it could be that you have unused signals. That is, the sender sends one signal for state 1, another for state 2, and never sends the third signal. And the receiver, if he gets the first signal, does the right thing for state 1. If he does the second signal, gets the right thing for state 2. And if he gets a third signal, then he's got some probability of doing the right thing for state 1 and the right thing for state 2. And it could be anything, right? So it could be anything in 0, 1. And it doesn't make any difference because it's never exercised. So here's a diagram of synonyms case. My columns are states, signals, and acts. And my arrows are telling you what the strategies are of the sender receiver or distributions. So here's synonyms. In state 1, the sender sends signal 1 with probability x, signal 2 with probability 1 minus x. X can be anything from 0 to 1. So here we have a whole line of equilibria under synonym equilibria. And then the receiver does the right thing on either of these 2, and then the rest just works deterministically. And here's the case of unused signals. Signal 2 is never sent, right? So the receiver does the right thing to get signal 1, the right thing to get signal 3. But if he gets signal 2, he has some strategy that's never exercised, right? This probability y does act 1, probability 1 minus y does act 2. note that these two lines of equilibria share a point. So that if x is 1, that means that I'm going from state 1 deterministically to signal 1. If y is 0, that means, or if y is 1, that means I'm going deterministically from signal 2 to act 1, right? So if those are both the case, I've got a point that's in both of these lines of equilibrium. The equilibrium structure of this game is very complicated. There is a whole component of such efficient equilibria. All of them have perfect information transfer, right? And it's all connected, right? You go from continuously all through these kinds of equilibrium. Now, we also have, of course, the equilibrium. Okay, well, then there can't be any evolutionarily stable structures in this game. Right? Any of these efficient equilibria, right, has guys that are right in the neighborhood that are equilibrium. So this is pointed out for the first time, I think, by Donaldson, Lackman, and Bergstrom in the Journal of Theoretical Biology in 2007, where they did an analysis of the equilibrium structure of such games. And it's general. If you have too many, if you have a lot of signals, right? This is always true. There never are any evolutionary stable structures. Okay, so things are getting more complicated, and Maynard Smith is not giving us an answer. You could have many states, and this may be a more common situation, especially in animal signaling. That is, there may be lots of states, but not so many signals available, right, for the signalers. Where you have a lot of states, but some kind of a bottleneck that the state information gets funneled through, either because there aren't many acts available or because there aren't too many signals, then you have a model of category formation. That is, the best you can have, the best equilibria are equilibria that lump some of the states together, put the states together in categories. In such games, there may or may not be evolutionary stable strategies. Okay, so I won't go through the details. Sometimes you can have, so there are, and sometimes there aren't. And finally, my third generalization, or fourth, or whatever it was to go away from common interest. So I go all the way away from common interest and assume that the sender and receiver have opposed interests. These are the payoffs for respectively sender and receiver for each of the state act combinations. And then the only equilibria that are possible in this signaling game are pooling equilibria, that is, equilibria with no information transfer. So you might say, so there's no ESS, but there's also no equilibrium selection, or not much of an equilibrium selection. There's more than one equilibrium. There are no ESSs. So I'd like to suggest that the right way to think about equilibrium selection is not with a static or quasi-dynamical concept like ESS or strict Nash or any of the 100 other equilibrium refinements that were put forward in the game theory literature when everybody was doing this, but with dynamics. And of course, the question is, what dynamics should you use? And I don't have a particular dynamics that I think is the right dynamics for everything, but here are some specimen dynamics in which interesting things happen. If you're wondering how you get equilibrium selection over evolutionary time in such interactions that are modeled as these kinds of games, then replicator dynamics is a reasonable choice. The more successful something is, faster it grows. Right? Things that are more successful than the average of the population increase their population proportion. Things that are less successful decrease their population proportion. If you assume that the payoffs are in terms of Darwinian fitness and the population is very big, then what you expect is what you get, and you get some differential equations, which are replicator dynamics. Okay? And I could say more, but I won't say more unless you ask. The other kind of dynamics I'd like to talk about is learning dynamics. And this is where you have two individuals repeatedly interacting. And they start out not knowing how to signal. And there are these repeated interactions. And there's trial and error learning. Okay? Lots of other learning dynamics are interesting. Right? But the one I'm going to talk about is trial and error dynamics. This is a version of reinforcement learning that was brought to the game theory community by Al Roth and Ido Arab in a paper on low rationality learning in games, but they trace it back to Richard Herrnstein and what Herrnstein called his matching law. Of course, if you read Herrnstein, the matching law actually means a lot of different things and so on. But this kind of reinforcement goes like this. There are a bunch of things you choose between, right? You might start out choosing at random according to some weights. So we'll assume that you have equal weights in choosing something. Like say that you're choosing between three things. You've got an urn with a ball of color 1, color 2, or color 3. You reach in here and pull out the ball. That tells you what to choose. Okay. You choose something. Then you get a payoff. Right? Payoff could be 0, could be something else. You take the number of marbles of the color of the thing that you chose equal to your payoff, and you put it back in the urn. So your urn keeps track of the accumulated payoffs, right? And then next time you reach in the urn, so you choose with probability proportional to the accumulated payoffs over history. Okay? That's the plain vanilla version of Roth-Arab dynamics. That's what we're talking about. I should say something more. I'm especially interested in low rationality learning to the extent that it works. Because the lower rationality, the more interesting it is if it works. Whereas usually in the evolutionary dynamics in these signaling games, you let a whole strategy evolve, right? Or if you have two populations, a sender population and a receiver population, a sender strategy and a receiver strategy. And those are the things that evolve. But in my learning model, I don't want to have the learners have strategy necessarily to start with, right? So they'll just have things that are stimuli, right? And they'll respond. So that means that the sender in the two-state case has two stimuli, state 1 and state 2. He's got an urn for each one. That determines the probability of sending signals. And the receiver's got two stimuli, those are the signals, and he's got an urn for each one. And they don't have to think about these things being connected at all, right? They just have reinforcement learning going. So you could do reinforcement learning directly on the strategies, but I'm trying to move down to a little lower, more primitive level and have it work directly on the acts. So, section 4 is equilibrium selection by dynamics in both of these things. And perhaps surprisingly, I think it's surprising, in the simplest Lewis signaling game, both evolution and learning converge to a signaling system with probability 1. For evolution, that means let's have all of the possible population proportions. Right? Put a uniform measure on it. Choose initial population proportions at random and run the replicator dynamics. Okay? For almost every point that you can choose, you converge to a signaling system. Okay? And that is due to the fact that the pooling equilibria component is unstable, right? And if you get perturbed off it in one direction, you go to one signaling system. You get perturbed off it in the other direction, you get carried to the other signaling system. Okay? So signaling systems just pop up spontaneously in that sense. That's shown along with other things that I'll mention a little bit later in an article by Josef Hoffbauer and Simon Hudiger in Journal of Theoretical Biology, 2008. It's also true in the reinforcement learning. You start these guys off choosing at random, and with probability 1, they converge to a signaling system. Okay? If you choose them off, set them off with equal numbers of balls for all their choices, right, in all of their urns, say 1 for each, but it doesn't matter. Then with probability half, they converge to 1. Probability half, they converge to the other. Right? If you start them out with unequal numbers, then with probability 1, they'll converge to a signaling system. Okay? And which one depends on how you start them off. Okay? So pretty strong result. And this is in a paper with 3 guys who collaborated in proving the theorem and me suggested the problem. Suppose the states aren't equiprobable. So this is the smallest departure you can imagine, I think, from the simplest Lewis signal. Okay. Then it isn't true anymore. Replicator dynamics sometimes hits an ESS, that is, a signaling system with perfect information transfer, but sometimes it's the pooling component. There's an analytic treatment in Hoffbauer and Hudiger, and what happens is the component of pooling equilibria, right? This is a line segment now, remember, is such that if you're in the interior of the space, population proportions, and you're near this component, but not at the end points, you get sucked into it. Okay? If you're at the end points, you get pushed away. So, so the component in the language of dynamical systems is not an attractor, right? Because it doesn't attract everything close to it. Right? And it's not an evolutionarily stable set. And you can think of all the refinement stuff that's been done in terms of evolutionary game theory or regular game theory to refine, right? And it isn't any of those things, right? But nevertheless, it attracts some proportion of the state space that has positive measure. Okay? And that positive measure gets bigger and bigger as the states become more and more unequal. Okay? So make the states very, very unequal, then it becomes quite likely that you get to no signal. Although if you don't make them 0, 1, the signaling systems always themselves have some positive basis of attraction. reinforcement learning. Sometimes it's signaling systems, sometimes the pooling. We now have ended the analytic results for these things, except for something more I'll get to about replicator dynamics modified. But certainly nothing more for reinforcement learning. And there's no published analysis even of this case for reinforcement learning. Though there's something you can say that's analytic, but let's say for public consumption, this is simply, from now on, it's all simulation, unless I say something else. Suppose we have n states with the states equiprobable, so we have three or more states with the states equiprobable. Now we've got partial pooling equilibria. Okay? We're keeping the states equiprobable to make it easy to learn how to signal. It's still true that you never hit total pooling, right? But it's not true that you don't hit partial pooling. Sometimes you get partial pooling. This is a simulation result. There's some partial analysis of a part of the game where you look at the component of partial pooling equilibria in this paper that I have with Bruce and Kevin Zolman that just came out in some things, where we can actually look at the surface and compute the stability properties of points. Things get attracted into it. With reinforcement learning, no analytic treatment, but simulations now again show partial pooling. Never hitting a total pooling equilibrium as long as the states are improbable, but hitting partial pooling equilibrium. And now, if you do this instead of 3-state signals and acts, and go up, to 9, 10 state signals and acts, then you hit various partial pooling equilibrium lots of the time. Now remember, these are cases in which ESS seem to be very good for equilibrium selection because they gave us a univocal answer. But the answer is wrong. So that's the first. In 2 states, 3 signals, 2 acts. Again, there's no analytic treatment. Simulations show that synonyms persist. Okay, so you could think you could get either synonyms persisting in your final results, or you could get synonyms withering away and unused signals. Simulations suggest you never get unused signals. Right? Synonyms always persist. So ESS didn't tell you anything, but dynamics is trying to tell you that synonyms is natural in this setup for synonyms to persist. If there are lots of states, so that the states have to go through a few signals, then we have dynamics of category formation. There's lots of interesting work on this now, I think. There's some papers by Jeff Barrett, the first one I think in 2007, in which he talks in terms of rather simple Lewis signaling games, in terms of category formation, conventionality of kinds. These are games in which you can get one set of categories or another set of categories, just the way things fall out. Natalia Komarova, Kimberly Jameson, and Louis Ahrens have a series of paper on evolution of color categories, where they have an evolutionary dynamics, and what's driving the evolution is the infusability of colors, so that you get filtered through a bottleneck, right? And you have only so many things that'll go through this bottleneck. But you want the categories to be separated in a nice way. So there's a topology on the states, right? And that influences the kind of categories that you get. I think the first one's in Journal of Theoretical Biology. And then there's a paper that I just saw recently. It's not published yet, but it's on the web by Jaeger, Metzner, and Riedel on what they call Voronoi languages, and they put their state space on a plane or something like that, and they have a kind of similarity metric that's the metric on the plane, and things get filtered through a small number of signals, and something like Komarova, Jameson, and Ahrens, they get natural kinds of partitions emerging on the plane, and actually these turn out to be Voronoi tessellations. That's why they call these Voronoi languages. So I think it's a rich area, and just a few things have been done, and probably a lot more things have been done. Okay, I want to go back to the game where I relaxed the common interest. Here the only equilibrium that was possible would be an equilibrium with no information transfer, because if the sender transfers any information, right, and the receiver wants to move it, and the sender wants to change the information, and so on. So you have a kind of arms race. The sender would like to deceive the receiver as to the state. Right? If we, for the sake of an example, restrict the strategies of the sender and the receiver here to separating strategies with two signals. So the sender doesn't ignore the state. The sender sends something deterministically, and the receiver does something deterministically. But now we look at a whole population of such senders and receivers. So there are different proportions of the population that have these deterministic strategies. You look how the population evolves. Well, there's a unique equilibrium, population equilibrium now, at a half. But this is just like matching pennies in evolutionary dynamics. If you start anywhere else, you don't get there, right? You go around and around. So given the strategies restricted in the way that I did, there's no equilibrium selection problem left because there's only one equilibrium. But that doesn't make any difference because you never get it. So equilibrium selection is actually the wrong question. The question is, what happens? Well, this is kind of a rigged up example, right? So is it good for anything? Really, I have a couple of examples. Elliot Wagner, who's writing a dissertation right now, has a working paper at the Institute for Mathematical Behavioral Sciences at UC Irvine, where he analyzes Spence's model of job market signaling. And the model has to be cut down a little bit in order to be able to be something that can be analyzed. But here's the sort of thing he finds. For certain parameter values, you have a lot of the interior being attracted to a face. And on the face, you get things just like matching pennies. So if you look just at the equilibrium structure, right, there are some equilibria, right? The good job market signaling equilibrium, right, in which the costs enforce honest signaling, is a point attractor, right? But it isn't that it attracts the whole space, or even most of the space, right? Most of it gets attracted to other stuff, and a significant portion gets attracted to cycles. So drug market signaling is a famous model in economics, Nobel Prize. There's a famous model of costly signaling in evolutionary biology called the Sir Philip Sidney game. Right? This is a model of chick begging for food. Right? Parents want to feed their chick. They want to feed the chick that's hungriest first. The chicks want to eat as much as possible. Right? So this is a game called the Sir Philip Sidney game, and Seaman Pudiger and Kevin Zollman did an evolutionary dynamic analysis of the Sir Philip Sidney game, and they find not most, but a significant portion of the state space gets attracted to a face, and you have cycles on the face. So it's like matching pennies on that face. So again, you never get to equilibrium. Well, these things are dynamically they can be perturbed if they change. But as it stands with this dynamics, that's the picture. So here's something that's worse. This is not exactly the best picture, but it's close because I couldn't get the best picture. This is a picture of a strange attractor called the Gilpin strange attractor in population ecology, and this is chaotic. That is, things sort of, there's an unstable equilibrium point. Things get close to it, and then they shoot out, and then they go around, and then they get close to it again, and then they shoot out, but in a way that you really can't predict, right? Rather than get something called a strange attractor. And Elliott Wagner found that you could get, a signaling game with not common interest, but with chaos that nobody particularly bizarre, such that you get attracted to a sub-simplex in which you get chaos that's like this, right? You get a strange attractor. This is in a two-population model, so it's Hamiltonian chaos because the population dynamics, the two population replicator dynamics is Hamiltonian. So this is a little more robust than the cycles because the cycles I showed you weren't limit cycles; they're not structurally stable. So you perturb them a little bit, and you can get them to spiral in, to spiral out. Not that that's okay. I have two further considerations, but is my time up? Or?
Well, in theory, but I think you should give us
Okay,
the
be very short. So I've already set up, maybe you should perturb the dynamics because a lot of the things I've showed you are not structurally stable. And what that means is if you change the dynamics a little bit, they change a little bit. Okay? And I showed you that already with the plane of pooling equilibria that collapse to a line. Right? In 2 by 2 by 2 states unequal. Okay? So you could perturb the dynamics a little more and that line would change, right? Depending on whether you may think you go out a little bit or in a little bit or whatever. So the most reasonable principal perturbation to try is to, in an evolutionary context, is to throw in a little mutation. In the large population model, there's a good model of replicator dynamics with mutation, called replicator-mutator dynamics, and things are known about it. That is, conditions for which it must converge, and so on. Some of them established by Joseph Hofbauer. And Hudiger and Hofbauer in this Journal of Theoretical Biology paper do this. They add a little mutation to the replicator dynamics. And what mutation does is it collapses that line to a single point. And that single point is now sitting there in the interior of the simplex of population proportions. And the question is it an unstable point, in which case you get restored the nice conclusion that probability one emergence of a signaling system slightly perturbed by mutation? Or is it stable, in which case it attracts some space, right? And you get the bad result back? And the answer is, it depends, right? It depends on how unequal the probability of the states are. If they're close to being equal, a little mutation restores probability one emergence of a signaling system. Right? But at some point, as they get more and more unequal probability, there's a bifurcation in the dynamics. And that point becomes an attractor. Right? It attracts stuff near it, and then two unstable points on either side. Two unstable equilibria appear on either side. Blah, blah, blah. Okay, so I could show you that. Let the game itself evolve. I should stop. Okay, so you could let the game itself evolve, but I'll leave that as a teaser.
Yes, you've got a lot of wonderful things here. You started out by running a $1 bill. Does adding expense to the signals make any difference?
If you just make a signal expensive, it doesn't. I mean, it doesn't make any real difference. Right? I mean, it makes some difference, right? Because if the receiver isn't paying any attention to the signal, then you'll send a cheap signal. But if the receiver is paying attention to the signal, then usually there's an equilibrium in which you pay the cost that you don't need to pay. And the only thing that makes the hobby stuff work is when the costs of the signals are differential between the states. So some state is cheap to send one signal and expensive to send the other. And if those costs are big enough, right, then they can enforce signaling.
And I guess one other possibility is that there's social or sexual selection for expensive signals. But I don't know if that would have any effect on social dynamics that this can uncover. I mean, presumably that's behind valuing elephants or things like that.
So the peacock's tail and things like that. So that can work, and I think you just put these things into the payoff function, and it's possible for it to work. But I also think that the hobby line is a lot oversold. Of course, everybody thinks the hobby oversold, but I think even it's more oversold because in a lot of these things there's been some focus as to whether you could sustain something in equilibrium using costs, right? And people have done models in which you can, but without looking at the whole dynamics of what goes on. And Sir Philip Sidney was one example of this, and you can't really make the argument on the basis of just finding one stable equilibrium.
If there were a cost to maintaining a capacity to signal, you would think that it seems like that would affect the model in which synonyms persisted as opposed to.
Louis Daring said that first time we did this in our seminar. And he said, put a little cost on all of the signals, and you'll find that synonyms will go away.
Well, not on the active signaling, but on, well, my intuition is not on the active signaling, but on having the capacity to make that.
Well, I tried all kinds of stuff, it didn't work. I mean, maybe there's something I didn't think of, but it really didn't work. If you had differential costs, I mean, the idea was you put uniform costs on, right? And then
Yeah,
that would
my
maybe,
intuition is the uniformity.
for maintaining something as an active signal, right? So that it's cheaper to have 2 active signals than 3, right? Okay, and you think, well, dummy, right? But the dynamics doesn't do that. I mean, you can put that in and it doesn't work, right? So you need something fancier than that to make it try out. Now there are models that you could have with some kind of forgetting, right, or finite population where types kind of die out. Right? And that can prune the number of signals. If you have many more signals than you need, and some of them aren't used very frequently, and you've got a finite population, then it can be that the fluctuations just prune the number of signals in the population. But that's a little delicate because if you have a finite population, you know, like this with guys dying, anything can happen, right? Anything can go extinct. So it's a question of relative probability. You have to do Markov chain analysis.
On the subject of synonym, a lot of real-world signaling systems and natural language. A lot of real-world communication systems, I'm thinking of natural languages, but also things like kinetic code, have some amount of synonymy in it. And I'm wondering if part of the explanation of the maintenance of synonymy might have to do with what happens when you introduce some noise into it. So has anyone looked at what happens in the Lewis signaling games with some noise so that a given signal once sent has a certain probability of turning into another signal before received? Because you would expect that when we know from information theory that if you've got noise, then you better have some redundancy. The most efficient thing will have some redundancy, which is in essence synonymy, because you can be able to.
Sure. I understand what you're saying. There's a lot of stuff done with noise, but there are a lot of noise. But the inference that it would be better, right, that it's what evolves, is not a good inference in general.
So just asking.
So you have to have the dynamics driving it, and the dynamics doesn't care what's better for the species, right? It just does what it does. So it's what's better for reproduction, what drives the dynamics, and that could drive the species into something that's bad for everybody.
So I'll be asking you to see what happens.
I'll tell you a model that I have, that I call a Condorcet model. A bunch of senders observe the same state of the world, but they observe it with some independent errors. And they all send signals to a receiver. The receiver now has to decide what to do. And the receiver, this is just driven by, say, reinforcement learning. So these guys, the receiver can't think. The receiver just gets reinforced. What the receiver learns to do then is to take a vote, like take a majority vote, which is the right thing to do. So this is noise and observation, but you could put the noise in sending the signals, and I think it would work the same way. So this is where the dynamics drives you to something that's pretty good for the whole group. But there's no reason to think that that's always
There is signal and the noise associated with it, as you were saying, would there be some way of recognizing some type of patterns that enable you to identify what could be the underlying real signal that is coming in? If you can manage to isolate the noise.
I had trouble hearing this exactly.
What I'm asking is, can you identify through pattern recognition if there is a certain associated noise with the actual signal?
The evolution of pattern recognition, I think, is a really important subject, and somewhere it comes in a little higher up in the evolution of signal, because that's when you want to when you want to look at patterns of signals, and I think that's probably how you're going to have to explain more complicated signals, the origin of more complicated signals, and you begin to recognize patterns, and that gives you compositionality of signals. Okay. But that's, I have some very tentative things to say about that, but that isn't very well developed at all. Bill?
I'd like to, the first thing I'd like you to do is to show us what you were doing with Sandy's Bell. And then I'll have a question that I want to get.
Thank you, Bill. So this is an idea to let the game itself evolve. And especially since you can get into nasty trouble if you don't have enough signals, why not invent new signals? This happens all the time, I think, in nature. And so, of course, you want to study this, but you need some sort of tractable model. The idea is to modify reinforcement learning to reinforcement with invention. We have an earn model of reinforcement learning.
So this is you're adding in the extra balls proportional to how much better the...
Yeah, that's the model. It's a model of reinforcement learning. Actually, it's kind of a model of finite population evolution too. Now, if you want to put something, if you want to invent something new, there's an earn model that was studied by a man named Poppy as a model for evolution, neutral evolution. We have lots of alleles that don't make it. And what he had was a polyurn with an extra ball in it. The polyurn has colored balls in it. There's a black ball in it. The black ball is a mutator. You reach in. If you get the black ball, you put it back, and you find a ball of an entirely different color that isn't in the urn. You put it in. And there's a potential infinity of different colors out there, so you can always do this. So this is Hoppy's urn. Now Hoppy's urn doesn't have reinforcement, but you can add reinforcement. Put it together with the raw data model. Now we have a model of reinforcement convention. We can make this into a model in signaling. That is, we equip everybody with, we equip the senders with Hoppy urns, right? If they reach in and get the mutator ball, they find a new signal, they try it out, right? The sender either does the right thing or not. If the sender doesn't do the right thing, the new signal is discarded, right? It's not considered as a potential signal anymore. But if the receiver does the right thing, then the sender considers it a signal. Puts it in each of the sender's urns, potential signal, right? The receiver's got an urn that is an urn for this signal, right? Potential signal. And that's how the process goes. So we know some things. The limiting number of signals in this urn model is infinite, which is also a model for the single Hoppy urn that you have an infinite number of signals. probability. But the number of signals grows slowly. It grows slowly down. So you can run the thing for 10,000 or 100,000 trials and end up with maybe 20, 50 signals, 20 signals, not a crazy number of signals. If you, I have another slide that says this. Oh, yes, players always learn the signal. You said not reading the part about it all being simulations. But, I mean, all of these pooling traps,
Yeah,
partial
so
pooling
this
traps,
holds for
all
all
of this.
these cases you were looking at.
Yes,
For example,
yeah.
the chaos one where you have all
Yeah,
this.
yeah.
weird- So just add
Players
this
invent their
little
way out
change.
of all the traps and learn the signal. So it'd be nice to have an analysis that,
Yeah,
but that's down the road somewhere.
Do you have any, any idea about why this modification should make such a
New
difference?
signals can give you any trap.
See, this is like, okay, this is like adding,
There are two ideas. There's Wayne's idea. You can fall in a trap and a new signal will let you get out.
okay.
And the other is you'll invent enough signals so you'll never get into a trap. There are two possibilities, or they could both be true. You can test them both by simulation.
Yeah.
You test Wayne's idea by putting you in a trap,
Yeah.
right?
Uh-huh.
And seeing if you can invent your way out. You test the other one by giving a lot of signals to start with and see if you ever get into a trap.
And so what
Of course,
happens-
theoretically you will, but it could be with very, very small probability.
And have you done, what happens when you?
Both are true.
Both, okay.
Both are true. You have enough signals, you have very small probability of getting into a trap. If you're in a trap and you can invent new signals, you can invent your way out.
Now, my actual, this has helped answer already in a certain way, but I still want, my question was maybe on the two basic kinds of dynamics. Now, one of the things that was happening in these finite cases, you were saying, look, the learning one is really light, a finite version of the replicator. But I want to ask you about how informative the two kinds of dynamics would be in these various cases. And one of the things that you're saying, most in this last thing is for these small number cases, they're sort of very similar anyway. Well, okay, we'll let you say that.
Yeah, they're very similar in some sense. That is, if you have, say, a fixed decision problem, like a bandit problem,
Yeah.
like you're playing two slot machines, more bandit problem, then you can prove that somebody proved, a guy named Beggs proved that Roth error of reinforcement learning converges to playing the better paying slot machine 100% of the time. To prove this, he used stochastic approximation theory. So the idea is that as this stuff piles up in the urn, right, the process slows down, right, and it gets, with higher and higher probability, it approximates closer and closer to the mean field dynamics. You can calculate the mean field dynamics, and the mean field dynamics is kind of replicator. So that's how he proved it.
Okay.
And the stuff that with P-mantle and so on, our theorem is proved using mean field dynamics. And if you look at the mean field dynamics in the way that this is set up, it's set up with some tricks and everything to get it into a forced place. There's a pooling surface, right? And the mean field dynamics on one side of the pooling surface goes to one signaling system, and on the other goes to the other signaling system. But then there's some, because it's probabilistic, then there are things you have to worry about, like whether it can cross, how many can't cross the surface, and there's a number of times that has to be proved, and then there's a question of what happens at the boundary, and can it converge to the surface at the boundary, and the off-the-shelf theorems don't apply at the boundary. That's a risk of variance. So it turns out to be complicated, but that's basically what's driving it. Now, of course, you could have, you might say, but I'm interested in people who are smarter, right? So if you want to design an algorithm that will always learn the signal in all signaling games, it isn't hard, right? But that's a different thing, If you want to say, here are people, animals, whatever, they're dumb reinforcement learners going to make a signal, that's my question. The engineering question is, well, can I design an algorithm that will always learn the signal? Well, here's one. In these signaling games either pay off or not. Right? The basic Lewis games mess with the payoff functions and the story, but the basic ones, you either win or lose, right? So your algorithm could be, if you win, you keep doing what you did last time. If you lose, you try something at random. Players do that, they always learn how to signal. So it isn't hard, but you'd like to know how these natural dynamics work.
Maybe you should explain the burning dollar.
I don't know. Malcolm has.
Yes, and in natural languages, a single word or a single signal can have more than one meaning depending on the context. They're completely different, unrelated meanings depending on the context. Is there a way of, has that been taken into account in terms of simulations of the kind that you've been studying?
Nothing like that, is it?
Yeah. Because that would require both sender and receiver to have some knowledge of the state of the world, but yet some further aspect of the state would have to be sort of communicated in the game. And they're just not.
So I don't see why you couldn't modify the basic games to take account of this, but none of the stuff that I know about is none of this.
Yeah, I was wondering whether that's a sort of function equivalent way of inventing new signals, giving old signals new meanings in some sense.
Well, I don't know. Certainly depends how you set up your context. In principle, it certainly seems right that if you give a signal more than one meaning, depending on the context, then you're doing more with a small number of signals. But then there's a modeling question. How do you actually make this model? What's its relation to the other models? Interesting question. Brad?
So what's the significance of the burning dollar?
Well, it's signaling for forward induction. You don't know about this? I've always wanted to burn
So this is a question about how things would go if you made your learners a little bit smarter, a little bit different. So as I understood the explanation of the reinforcement learning, what happens is in the event I get a payoff, I add the number of balls equal to the payoff, right? Which is kind of a straight rule, sort of, you might say, right? You could imagine agents having different attitudes toward sort of inductive risk, you might say, right? So that, you might sort of slow down the learning process by adding sort of fewer balls. With the successor, you might have a kind of case where you'd add sort of a large number of balls, people would learn faster. In fact, and I'm curious if you think that would make any real sort of difference to these results. If you had the signalers sort of with different who are sort of disposed to learn inductively at different rates. Some fast, because I'm taking it sort of the more balls I put in, the more So
that
I
slows
said-
you down, yeah.
But-
You want to know what happens if you don't slow down, perhaps?
Well, I mean, I guess I'm just sort of curious if there's going to be sort of difference here with respect to the question of whether or not you end up fully in equilibrium or not.
So I can say a couple of things because a couple of things are relevant. One is so this form of reinforcement learning slows down. And really the stochastic process sort of fluctuates around some mean field equation, and there's a term that slows down in proportion to how far out you are, roughly in proportion to time. Keep that as well. There are other forms of reinforcement like the Bush-Mosteller, the plain vanilla Bush-Mosteller model that doesn't slow down at all. Those guys learn too fast in the sense that they can grab onto something that's suboptimal and do it forever. So in the two-armed bandit problem, Bush-Mosteller learners have a positive probability of playing the inferior slot machine forever. And the same carries over into these evolutionary, into these game theory models that you can lock onto things that aren't Nash Equilibria. All sorts of things are possible. They may not happen very often. Now, I did run simulations with basic Bush-Mosteller, and with reasonable parameters, it learns the signal pretty well. But it won't always. So that's part of the answer, and that's in the step size of the stochastic process. The other part of the answer is what about the initial probabilities? So I make the initial probabilities, I put 2,000 balls in the churn, right? The reinforcements are 1, right? Then you're going to learn very slowly, at least in the beginning, your priors are going to be very, very heavy. But if I put in 1/100th of the ball in here, right, then, or reinforce, multiply reinforcements by 100 times, then the prior stuff is going to be swamped out very fast. Now it turns out, Roth and Arab, in their experiments of using this stuff to learn zero-sum games, looked at a wide variety of prior weights and found they didn't make any difference. But it turns out that in signaling games they do. And very small prior weights are very good for learning how to signal. It turns out. If you have very small prior weights, then individuals tend to lock onto successful pieces of the signaling system.
Well, let's thank our final Arsenal one more time.